of anniversary lectures and of Sectional Committee 4. Hello, can you hear me? Okay. Uh, this this program of having anniversary lectures for each sectional committee was started last year, and this is the second term on which, for every sectional committee, two persons have been invited to deliver lectures. The first talk in this case is Professor Somnath Dasgupta, and he will be speaking on the advent of plate tectonics and the supercontinental cycle selected Indian examples. Professor Dasgupta is a very well-known and versatile geologist of this country. He is currently INSA Senior Scientist at ISI, Kolkata. He served as a geologist in Geological Survey of India, then as a professor in Jadavpur University for a long years. Then he became a professor at ISER, Kolkata. Then he had a stint as a vice chancellor of Assam University. Then as a Ford Foundation chair professor at Jamia Millia Islamia. He obtained his PhD degree from Jadavpur University in 1979. He is a fellow of all the three National Science Academies and of the World Academy of Sciences. He is a recipient of National Mineral Award from the Ministry of Mines, Krishnan Medal from the Indian Geophysical Union, INSA Teachers Award, D.N. Wadia Medal from INSA, and J.C. Bose National Fellowship from DST. He is a fellow of Alexander von Humboldt Foundation and also served as a Mercator guest professor at the Ruhr University, Germany, as JSPS visiting professor, to Hokkaido University, Japan, as a visiting scientist at the University of Arizona. May I invite Professor Dasgupta to start his talk.
Thank you, Professor Banerjee, and hello everybody. It's a great pleasure and a privilege to address you from this August forum. So I'm going to talk on a topic, Advent of Plate Tectonics and the Supercontinent Cycle, with some selected examples. Now, only the last part, the selected example, is actually the work of our group, and the first part of the lecture is actually of a general nature to introduce to a general audience one of the burning issues of earth sciences that we have today. That's the plate tectonics. In the part one, we discuss about when did plate tectonics start and what was the tectonics before plate tectonics and why should we be interested? What are the approaches of investigation? In the second part, I talk about the supercontinent cycle. How does it influence the evolution of the Earth and what is the relation between plate tectonics and supercontinent cycle? And the third part, we discuss some of our work related to the Indian examples of supercontinent assembly and breakup. So I start with a general cross-section of the Earth where the pointer is not working, where I show a cross-section through the Earth. On the left side, I level the composition of the compositional variations of the Earth with depth, and on the right side is the rheological variation with depth. And for the purpose of the present talk, we will be mostly interested in the upper part, that's the lithosphere, asthenosphere part of the Earth, and the lithosphere is rigid, the upper thin crust of the Earth is rigid, and down below we have the asthenosphere and the lower mantle, both are less rigid and support mantle convection. Now,
how is the pointer is not without pointer, how can you say?
It's working, but nobody can see. Anyway, I can continue, no problem if you are comfortable with this. So actually, uh, just to emphasize that I'm talking of a very contemporarily unsolved problem in earth sciences, that is, when did plate tectonics actually start on the planet Earth? Now, this was embodied in the National Science Foundation Vision for Earth Sciences Research, one of the 10 topmost problems, outstanding problems in earth sciences. It is not just because the NSF told us to do, but we are doing it for over last 20 years to solve these issues. And at the end of this lecture, I think you will find that more questions are raised than answers given in this talk. So the issue is again that when, why, and how did plate tectonics start? So why it is important to understand the Earth's tectonic regime? That's the first question that we have to answer. Tectonic processes are essentially the means by which any planetary body loses its heat and its interior differentiates, like as we know about the crust-mantle differentiation. And the understanding will provide critical information about the thermal, mechanical, and chemical evolution of the Earth's interior. Secondly, it exerts first-order control on the evolution of atmosphere, oceans, climate, and natural resources. So are all encompassing because they contribute to the critical to biological activity and the modern society. And thirdly, it also helps us to understand the localization of major physical processes responsible for geological hazards like volcanism, tsunamis, earthquakes, etc. So both from a theoretical standpoint as well as practical usage, we need to know about the tectonism operating on the planet Earth. So just to emphasize that this is an outstanding problem, you can see that several workers have suggested the time of initiation of plate tectonics in a wide range of ages, starting from 4.2 billion years to 0.85 billion years. Now, I request the non-geological audience to be acclimatized with the usage of words billions and millions now onwards. We will not be talking of years anymore. Now, so the issue is that you can see that over the last 20 years or so, so many authors predicted so many times of initiation of plate tectonics. Now, why? My simple explanation is that they used different lines of evidence to come to the conclusions, but never tried to get a holistic picture. And so far, we have not attempted that. And that is why it is considered to be an outstanding problem and we have to solve it in future. Well, the modern day plate tectonics is what we have today is by which the rigid outer layer, what I introduced as the lithosphere, is broken into fragments, which we call plates, and they move in horizontal motion with respect to set axis of rotation at a set rate and direction, which results in a linked system of involving different types of plate boundaries. And most of the deformation that we see on the planet Earth is concentrated along the plate boundaries. And two important, and this is a cartoon picture of this, and you can see that this is the creation of the plate where you, mostly from the mid-ocean regions, and these arrows are the mantle convection pattern. And as we move from the mid-ocean regions and go towards the subduction zones where the plates descend back into the mantle, in between we may have deep mantle plumes coming up onto the surface producing volcanism like in Hawaii. Now, these are the different methods of heat convection, and the lithosphere transmits heat by conduction largely, but below that we have extensive heat transfer by convection. Now, 2 points need to be reminded us. That one thing is that plate tectonics require global network of plate boundaries or the zones of deformation, separating multiple plates of rigid lithosphere. So it has to be a global network. And the second point is very important, that regions of localized subduction are not indicators of plate tectonics. So to emphasize this point, plate tectonics needs subduction, but subduction does not necessarily mean plate tectonics. So we have downward motion in the Venus, we have evidence of tectonics in the Venus, but that's not plate tectonics. Plate tectonics we have on the planet Earth. And oh, sorry, I didn't realize that. So this is the general picture of the different plates that we have and the plate boundaries, and as you can see that these are the plate boundaries are the areas of intense deformation, seismic activity, volcanism, etc., etc. And the interior of the plates are more or less rigid and more or less undeformed. I mean, we do have deformations, but not to the extent that what occurs at the plate boundaries. Now, geological evidence suggests that plate tectonics was not possible in the initial early Earth. One of the reasons is the prevalence of dome and messine structures in older terrains, like this kind of thing where you have a granitoid dome rising and the synclinal keel of the greenstone belt sinking. These are the kind of exchange of mass that is happening with depth, but this is something like a domal structure. You can see it will be on the surface a domal structure which is not a defined plate boundary as we see in plate tectonics. And this has been shown to be existent in Dharwad Craton in South India as well. Other thing is that some characteristic rock assemblages, diagnostic of plate tectonics, are absent in the early history. There are evidence of extensive plume-related magmatism in the early phases of the Earth's evolution. And most importantly, the underlying reason is that the mantle temperature was hotter in the early Earth. And therefore, it did not support plate tectonics. So, two issues that are important to decide about existence of plate tectonics in early Earth is that the hotter mantle temperature, and a second problem, which is a real problem for us, is that we are treating with very old rocks. So there is always a preservation problem. It is likely that many of the evidence have been lost. So we don't know about that. This is an uncertain parameter that we have to keep in mind. So it imposes some kind of uncertainty in our conclusions, but we cannot do anything about it. And so the Earth has, you can see from these plots that in the old ages Archean, the mantle temperatures were substantially higher than the younger Earth. The red dots are the kind of a type of mantle magmatism that occurred only in that period, and the liquidus temperature of these mantle magmatism shows that it must have crystallized from a very high temperature, which was not available later. So the reason, that is why we think that the early Earth was much hotter compared to the present. Now these are some general statements that I have made, that is how the Earth loses heat. Now, the Earth cools by transferring heat from the interior to the base of the outer lithosphere by convection, but within the lithosphere, the transfer of heat is mainly by conduction or advection of heat through migration of melts or fluids, but not convection sensu stricto. And finally, the heat is radiated into the space through the atmosphere. That's why I said that there is a connection with the atmosphere, with the interior of the Earth, and heat loss process drives all tectonic activities that we see on the geologic processes that we see on the planet Earth. So I look at some of the evidences now. So these are metamorphic evidences. So we have metamorphic rocks, and the pressure temperature of metamorphism defines three different kinds of metamorphic pressure temperature ratios: red, yellow, and blue. Now, if you see the blue one in particular, the blue one is a high pressure by low temperature or low temperature by high pressure metamorphism. And this particular blue one, as you can see, that they occur in the young Earth. This type of metamorphism is only seen in the young Earth, but it's not present in the old Earth. Now, why it is important? Because it is high pressure, low temperature, means that you have to transport crustal material to great depth and bring them onto the surface by a process which we commonly refer to as subduction, associated with plate tectonics. Now, this was then not there before this age. So this shows that this typical process of subduction related to plate tectonics possibly started much later. This is the early part of the Earth, nearly 4.6 to 3.8 billion years, and this is about 1 billion year, and then this is about 500 million years. So you see that this type of metamorphism increases in abundance from 1,000 to 500 million years. This is the same thing shown, and you can see now we have two distinct changes where these circles appear at this age about 2,700 million years, and then you have an abundance of these circles from 1,000 to 500 million years. So we have two different regimes which are distinct in the evolution of the Earth's history from metamorphic rocks. The other changes during 3.2 to 2.5 billion years ago were the changes in the style and chemistry of magmatism, changes from the TTG suit, that is the tonalite tronjamite granodiorite suit, to potash-rich granodiorites. Then we have a change in the inclusion pattern in diamonds from peridotite to eclogite. Eclogite is a high pressure rock which appears only at less than 3 billion years from now. And also we see a lot of other geological changes which show that the period from around 2.5 billion years could be very important in the history of the Earth. So if the early Earth was hotter and could not sustain plate tectonics, then what could be the tectonics at that time? Now, although I am showing this as cartoon diagrams, but these are all mathematical models, and they have been computed based on the rheological properties of the material, the temperature of the Earth, the heat production values calculated or assumed, and these are all, I think Professor R.N. Singh, who will follow me, will develop some of the mathematical principles behind calculation of these. Now, what happens here is that we start with a initial magma ocean that we all agree that it existed in the early stages of the Earth's evolution. This is followed by, and the magma ocean pushes some of the lava to the top, producing an volcanism on the surface, and that volcanism forms volcanic rocks which form the crust of the Earth, and this model is given the name heat pipe model. And recently, very interestingly, I was reading that similar models have been imposed, have been interpreted for some of the satellites of Jupiter. So there is a similarity there, and then this is followed by the deeps and plumes, where you can see that this material sinks through, this material goes up as in the form of plumes, and this material sinks in the forms of drips. Now, this dripping is because of Rayleigh's instability, Rayleigh-Taylor instability, density driven. This is not a subduction sensu stricto. And then this material can be detached when we call it delamination, and the material goes down. So the summary of this is that we have to make an exchange of material from the interior of the Earth to the top and back. Now, the transfer from the interior to the top is by plumes, like these things, and from the top to the down in the form of drips or delaminations. This is how we exchange, the interior of the Earth exchanges matter to the surface of the Earth. And this is the model from in further details of this model, where we have this initial model of heat pipe model, where you have plumes and drips, and this was followed by some amount of horizontal movement, as you can see, and local subductions, where the lithosphere was going down a bit now, but it was not going down to a level like this in the modern plate tectonic cycle. So it started sinking, but not this much. So we understand that the transition from this heat pipe model to the modern plate tectonics happened via an intermediate stage of transition of sluggish mode tectonics. And this is an alternate scenario which came up recently, about 5 years back, where these authors, they showed through numerical modeling, that the early, before 3.2 billion years, we had this heat pipe model, or which we call also the stagnant lid model. But after that, we have a situation where the subcontinental lithospheric mantle and the lower continental crust gets peeled off from the rest of the continental crust and go down, which they call it lithospheric peeling. At the second stage, this is detached from the crust, the lithosphere, which they call is slab break off. And finally, in the modern plate tectonics, the slab breaks off at greater depths. So we have a transition from peel back to shallow slab break off to deep slab break off. These are the transitions that this numerical model gave rise to. Now, people have tried to do these things through forward modeling. I think Dr. Singh will talk about the mathematics behind this. You can see the models where we have this kind of situation. On the right-hand side panel, the diagrams show that there is extensive melting in the red colored, extensive melting in the hot earth. Now, the mantle temperature decreases from right to left. Now, in the panels, you can see this is delta T. Delta T means the modern current mantle temperature and the existing mantle temperature. That's the difference that they have plotted. And the H stands for the heat generation using the radioactive elements. And for various functions of heat generation and mantle temperatures, you can yourself see that the evolution with time from bottom to up is the increase in time, which is given in million years, how the tectonics changes. And one thing is very clear, that here is no subduction, here is limited subduction, and here is real subduction, where the ocean, the lithosphere goes down deep into the mantle. So with lowering in temperature, it happens like this, and with lowering in heat production, plate tectonics come into existence. So this is a numerical model, and the same different group of workers, they showed that this numerical model also, as a function of mantle temperature and heat production, the stages are from the top to the bottom, is that the slab break off, peeling off, and then delamination or drip. So it's basically the material is going down and affecting mass exchange with so the mass is recycled back into the mantle, and then somewhere they come up in the form of plumes like that. So there is a continuous exchange of material from the deep inside to the outside. Now, the one big issue here is that these are thermomechanical models. But the composition of the chemical parameters are only taken rather less in consideration, particularly the amount of fluid, the variation in the composition, those factors, because it's really a multidimensional mathematical analysis. I think that people are trying to do that, to incorporate all the parameters into the computation to come out to some. So the fact that these numerical models have not taken all the factors, so they diverge in the final diagrams. So we have differences in opinion here, but we come to a general conclusion that we have a no subduction regime to pre-subduction to the modern subduction regime. And this is as a function of the delta T, that is the delta T is the difference between the temperature at that time and today, and this is on this axis, the y-axis, the heat production values are plotted. So this is what we get, and the consensus resolution as of today could be that we have a stagnant lead to start with, followed by around 3.2 to 2.5 billion years ago, there was a transition into sluggish mode of tectonics. Some people say it is peel-off tectonics or drip tectonics, but there is a transition, and from 2.5 onwards, possibly plate tectonics set in. But yet, the full form of plate tectonics possibly set in at around 1 billion years, not before that, as we know today. this is the present understanding. But you see, there's a huge time gap, 2.5 and 1 billion years. So we are yet to come to any consensus regarding these issues. Now come to the second part of the discussion where we talk about the supercontinent cycle. Now this is what Tujo Wilson pointed out long back. This is known as the Wilson cycle in the sense that we have a stable continent and then which is rifted apart by extensional forces where an ocean basin forms, and then these ocean basins get subducted. So we have then this two comes together and finally they join together to form a continent. So you will see, you start with a continent and come back to a continent. That is why we call it Wilson cycle, and this is what is the supercontinent cycle when all the continents came together. So I'll skip this because the chairman is pointing out 5 minutes? 10 minutes, okay. And so why supercontinents break? These are possibly the continents are low conducting, heat conducting abilities. So possibly the mantle heat accumulates at the base of the continents and that causes breaking up of the continents. During supercontinent formation, what will happen geologically is that the sea level will be the lowest because all the parts will become continents. The terrestrial deposits will be low preserved, and marine deposit preservation will be less. There are less of marine sites, and then we can expect extinction of marine life. And now large continental masses will lead to higher albedo, glaciation, and cold climate, particularly in the equatorial region. And during supercontinent breakup, the opposite things will happen. This is a model, numerically again computed model of sea level variations with time. And you can see that during the assembly of the assembly period, the sea level goes down and then it goes up during breakup. Now, I am not sure about the quantification of these things because a lot of assumptions have been taken into modeling. Nevertheless, it gives you a general picture. Now, supercontinent formation and breakup has also been related to proliferation of life forms. By no means I will say that the supercontinents were responsible for proliferation of life forms, but they possibly created an environment where life could proliferate. So these are the things that you should expect, that during the supercontinent assembly, vast mountain belts will form and they will provide nutrients to the ocean basins by weathering and erosion. That will cause explosion of cyanobacteria and algae to increased oxygen level. And during breakup of supercontinents, deep rift valleys will form with increased hydrothermal activity, producing chemical environment favorable for the proliferation of life forms. And possibly you might be aware that one of the hypotheses or the origin of life form is below in such a I mean to say a rift valley, but it's not an continental rift, but an oceanic rift in the sense below the mid-ocean ridges, hydrothermal vent activity produced life forms originally. That was one of the hypotheses. So this is the history of the supercontinents in the last 3 billion years. I will request you to just concentrate on this. Colombia, that's about 2 billion years, Rodinia and East Gondwana and Gondwana, because this is where our continent, India, traversed. India never was a part of this particular trajectory. Okay, this is just an evidence that we get lot of geochronological data on the timing of the supercontinent formations, because we need to remember that geochronological data records tectonic, magmatic, metamorphic history. So events, so naturally these are the times when major such tectonic events happened. This is the picture of Columbia, which was accreted between 2.1 to 1.8 and broke up around 1.5. And please have a look to India, North China, and East Antarctica here. This is the configuration. So India was close to East Antarctica. If you go to the next supercontinent, again, you will see that India was close to Antarctica, but the others changed position. For example, North China, which was close to India, has moved on the other side. This is the third supercontinent, Gondwana. Here again, Indian shield, or the India was close to East Antarctica. Now, all these three slides show that India and East Antarctica were close for over 1.5 billion years. This is the part. And the last one is Pangaea, from which Alfred Wegener postulated his hypothesis of continental drift. So we come to the Indian example, and what to better example is from the Eastern Ghats belt, and we are sitting somewhere here in Visakhapatnam, and this is Visakhapatnam, and this is the geological map of the Eastern Ghats, which shows a continuous belt of rocks from Bhubaneswar down to Ongole in Andhra Pradesh, 200 kilometers north of Chennai. And these are the different types of rocks that we find in the Eastern Ghats. I'm not going to bore you with the names of the rocks, but this is how it looks like. But if we do neodymium isotope analysis then we get this picture that the Eastern Ghats belt is not continuous, but each part, there are 4 parts which are called domain 1, 2, 3, 4. They have different ages of the protoliths. That is, the original rocks are of different ages. So the apparently continuous Eastern Ghats belt is divided into 4 neodymium isotopic domain. This is the work from 2001. And then what we did over 20 years is to calculate the pressure, temperature, time, history of evolution of each of these so-called domains. And these are all metamorphic rocks, so what we are determining is the pressure, temperature, variation of pressure, temperature, and with time of these rocks found in different domains. And you can easily see that the domain 1, 2, 3, and 4, they have different kinds of pressure, temperature paths. And since each pressure temperature path represents a particular tectonic style, so we can interpret the tectonism with the help of these. And these are very robust in the sense that, of course, geochronological data is through uranium lead mostly, and the pressure temperatures, etc., were calculated through phase equilibrium considerations as well as thermodynamic calculations of pressure and temperature. So these are quite robust, and you can see that each path is different and the timing is different. Please look at the timing, which, although you can see they are reaching at the same temperature and pressure, this blue curve is happening at 1,000 billion years, and the red curve is happening at 1600 million years. So they're reaching the same pressure temperature but at different times. And the evolutionary path is quite different. So from these we interpret the history that the first domain, this is the domain here, domain 1, we conclude that the Dharwar Craton of India and parts of East Antarctica approached each other at around 1800 million years. Now each age is constrained. And then by 1540 million years, they came together as a part of a single continent where only this part of Eastern Ghats became part of the Indo-Antarctic continent. Just 3 more. And this is the second domain, that is this one, the green domain, that is the Vishakhapatnam domain, I should say, because I'm standing here. And here, an ocean basin formed between East Antarctica and India, and then a renewed collision happened around 1000 million years, and by 900 million years, all of them became together. As you can see, that all of these blocks became together as a single continent. And not only Eastern Ghats, this is the scenario at 1 billion years when the different parts of India, like the southern Indian block and the northern Indian block, got together with the central Indian tectonic zone and so on. And this is how India looked like at around 1 billion or 900 million years ago. You can see huge white areas. These are largely the Deccan traps, which came much later. The third block, Chilika Lake, produced some interesting results. Its pressure temperature path was completely different, so we assume that it was not a part of India at that time, and possibly there was a strong similarity with the Pritz Bay region in East Antarctica, and so it is concluded that Chilika Lake area became part of the Indian continent by around 500 million years ago. So we have from the Eastern Ghats, 3 supercontinent histories: Colombia, Rodinia, and Gondwana, all recorded here. And this is what India looked like in 500 million years ago, when we still have this white area. That's the Deccan trap, the Deccan volcanics, which came much later. So the last part of the talk was largely our group work, and for that of course, I'm thankful to all the funding agencies as well as my students and collaborators, and thanks INSA for inviting me to deliver this talk.
Very nice talk. I had one question. Yeah. So, from thermodynamic point of view, so question is that if 2 things are coalescing, they must be gaining free energy by doing that.
Yeah.
But here, when you have these different blocks sort of colliding, what is the driving force? I mean, why are they sort of joining together? Free energetically, what do they gain by doing that?
Actually, this is an accretionary process. When the 2 things are by force, they're colliding together, and then they're rising to compensate that. So like the Himalayas that formed because of the collision. So it is more of the kind of that it is a physical process that is happening here.
So this Eastern Ghat, is that a result of that collision?
Eastern Ghat is actually, it is the collision in 3 stages. It started during the formation of the first supercontinent, that is Colombia, 1600 million years ago. and then culminated at 500 million years. So about 1 billion year history is preserved in these rocks. We could see outside.
Nice. Okay, thank you.
Any more? Many questions? No. Okay. Please.
Thank you, sir. Wonderful talk.
Thank you.
I'm not an expert in geology, but just I am curious about knowing about the Shillong Plateau in northeast India, which is considered in some writings I read that it's a part of the Deccan Plateau, a scattered rock there.
No, actually, the
Yeah.
Deccan Plateau is much younger. Deccan Plateau is much younger. Shillong Plateau is earlier. I mean, this is, I think, during the tertiaries that this was uplifted. It's slightly younger than the Deccan Plateau. Deccan Plateau is much little younger.
Okay.
But the question is that the Shillong Plateau is not related to this. Shillong Plateau is related to the Central Indian tectonic zone extending into the Indo-Burmese arc, and in between there was this Dauki fault which raised the Shillong Plateau. So that's a story that is quite different from what I discussed here.
Okay, thank you. I will have some more interaction.
Thank you.
Okay, I think we are short of time. We cannot have too many questions now. We invite now Professor Dr. Rishi Narayan Singh for Dr. Rishi Narayan Singh, please come over. Yes, for your turn. Professor Singh is a visiting professor at IIT Gandhinagar in Gujarat, and he has spent most of his life in National Geophysical Research Institute. He obtained his BSc and MSc degrees from the Banaras Hindu University in 1962, 64, and 69, respectively. He joined National Geophysical Research Institute, Hyderabad, in 1964, and made significant contribution in modeling of geophysical and environmental processes. He constructed models of thermal and rheological structures of Indian continental lithosphere, of processes underlying formations of Kadapa Basin and Charnokite rocks of southern Indian craton, and isostatic flexure complexion mechanism of Afnasi Nitikin seamount in slow spreading Carlsberg and Chagos lacative oceanic ridges and fracture zones of Indian oceanic lithosphere. He contributed to modeling of groundwater dynamics and fate and transport of contaminants in the environment. He participated in institution building in forming of CSIR Center of Mathematical Modeling and Computer Simulation, Bangalore, which he later headed in 1969, 96-99, and he served as the director of National Environmental Research Institute, NERI, Nagpur, where he initiated the frontier researches in integrated quantitative physical, chemical, and biological aspect of environmental processes during 1999 and 2003. He was CSIR Emeritus Scientist during 2005 and 10 and INSA Senior Scientist between 2010 and 15, both at NGRI Hyderabad. Since 2015, he is a visiting professor at IIT Gandhinagar, where his teaching research focuses is in a modeling of Earth's surface system. For his research work, he has been awarded with Shanti Sharoop Bhatnagar Prize of Council of Scientific and Industrial Research, National Award in Geosciences and Technology of Ministry of Earth Sciences, and elected to the Fellowship of Indian Academy of Sciences 1988 and Indian National Science Academy in 1991. Now with these words, I invite Dr. Singh to start his talk.
Thank you, Dheeraj, for your very kind introduction. This topic was given to me by the sectional committee. I have only polished it, so if it goes well, then he is responsible otherwise. Okay, so this is about mathematization of Earth system science. You saw Earth system science described by Dr. Dasgupta. So he showed you a lot of numerical results, and I will show what kind of mathematics has been used to derive those results and some more. So I will introduce the subject of mathematization. Then how do you see Earth? See, Earth was looked as a fixed view. Everything was static. And now Dr. Dasgupta presented to you a very mobile Earth. So how this picture changed from fixed to the mobile Earth? What led to that? And how all those mobility led to two processes. One is climate change and another about origin of life. And I will end with how this trend, how things are going in future. Okay, so in Earth system science, focus is on the relationship between components. Not only detailed study of components, but how components are related to each other, what kind of interaction takes between them, what exchanges, energy, mass takes place between them. So those arrows are very important. And at the center of our system science is a biosphere, where we are part of that biosphere. So how life evolved, how life is maintained, what will happen to life, how life changed the Earth, all these are the issues of the Earth system science. So why mathematization? First thing is that in mathematics we have precise statements. There is an algorithm, there is a proof, there is a quantification, there is axiomatization, there is idealization. The kind of heterogeneity which Professor Dasgupta showed, very difficult to model. So you have to idealize it in something which you can work out. And most of the laws of nature are in these forms, a family of functions or a differential equation or an extremum principle or a symmetry group. And as usual, everybody is envy of physicists. Everybody wants to be like physicists. And geology was a historical science. So they geologists also started with mining to start with, and geologists also wanted to be like physicists. And I will show you where that envy has led to. Very profitable exercise. Now, why physics is mathematical? So I quote Bertrand Russell, physics is mathematical not because we know so much about physical world, but because we know so little, and it is only its mathematical properties that we discover. So if you look at Dr. Krishnamurthy's talk, he took a Hamiltonian, and he derived everything from that Hamiltonian. He twisted, turned, rounded, approximated Hamiltonian, and got properties which were observed. So basically, it is the physical properties, mathematical properties, which you discover. Nothing else you discover. So we will see how this happens in earth science. And if you look up great mathematicians, like there are mention of names like Newton, Bradley, Delava, Laplace, Fourier, Gauss, Bessel, calls to mind not only a long list of inventions and discoveries, but the most important part of mathematical research. In its dynamical and physical aspect, Earth was to them the principal object of the research. So not only geologists, all these great mathematicians, they studied the Earth, and our knowledge has accumulated out of that. Okay, now, as I mentioned that geology started with mining. Out of natural philosophy, the one subject came which was mining. So I have a figure of one Newton, another Lyell, another Hutton. Lyell and Hutton are two great geologists. And they were influenced by Newton's ideas. And Lyell, he developed a principle of uniformitarianism. Means if I want to interpret past, I must interpret that past as an assemblage of what I am observing today. If I have not observed anything today, I cannot use that observation to the past. So like what Dasgupta discussed about East Coast, he never talked of any process which is not being observed right now. It is being observed somehow. So he said present is a key to the past. It can be also mean that the physical laws which we are using now, they have constants. They have remained the same in the past as they are now. Say gravitational constant. It has the same value 4.5 billion years as it is now. If it is not so, then Earth will be expanding, which we don't assume today. So that was real, and this Hutton, he also applied, but he took a steady state model. We find no histories of beginning. Like at t.0 of Earth, there is no evidence left. And where Earth will end, we can't find out. So he assumed that he had no evolution in his model. So there were these two views very prevalent among geologists. And imagine Hutton's book name, Theory of Earth, with proofs and illustration. He was talking of proofs. So they were all borrowing language from physicists. So how this now after, sorry, I want to go back. So the Newtonian mechanics ideas led to what is called fixist view. I will show you just now. But then there were other laws like thermodynamics and heat conduction. So here they said, no, Earth is not in steady state, Earth is evolving. And Lord Kelvin, Darwin, their ideas about evolution was used in the Earth science. So that is Fourier. He gave the theory of heat conduction, whose proponent was Lord Kelvin. Okay, so how do we use mathematics to find anything? So there are three routes. One is Newtonian paradigm. Here, analytical methods, we write solutions in terms of elementary functions or special functions. You saw in case of Dr. Krishnamurti, he had little more complicated operators. Then there's called qualitative modeling. Here I can't construct the solution, but quality of solution I can find out. Like I say, is it stable or not? Is it periodic or not? It is giving chaotic or not? And third is algorithm modeling. Here we give only algorithm. We don't prescribe any other numerical scheme. How we could leverage another thing. Now, Earth system knowledge has grown by applying all these three methods, whether Newtonian paradigm or qualitative modeling or algorithm modeling. So let us look at this picture. On the left, you find fixism. Whatever continental configuration which is have now has remained so in the past. And on the right, you see North America, South America, and Africa together. It means in the past, they have come together and they have been split. And a long list of people are fixist and another were mobilist. And there has to be great debate between them and great fights between them. Same data was being interpreted by them either fixist, means things came from below, mobilist, things came from side. So let us say how they got the fixist idea. Here's the great Harold Jeffreys. He was using gravity equations for tides. He was using elastic deformation equation to find out earthquake waves. And then people were finding electrical structure of the Earth's interior by using Maxwell's law of equation. And imagine there is no circulation term in these equations. So whenever they applied these models, they got a fixed structure. So there was no circulation in their model, so they can't prescribe circulation. Now, so fixist model was inferred by using gravity and elasticity theory. Mobilist model needed Earth's interior, newer conceptual development, and as Professor Gupta showed you, that mass now is circulating inside the Earth. And for that, I show you 4 pictures. How the attack used to be between them. Now this man in 1861, he gave this fit. It means it were separated, they came together. Then 1915, Wegener, great meteorologist, gave that fit. He was ridiculed. This man was ignored. And that man, 1920, he was attacked for this, giving these figures. But when Bullard in 1965 gave this fit, he was lauded. Same result, but why it happened so? Now what Bullard did, he used Euler theorem, means any movement on the surface of the earth can be explained in terms of pole, a rotation around a pole. And by the time computers available, so this diagram was built by computer, not by hand as people were doing. And this is harbinger of the plate tectonics, which Dr. Dasgupta has been telling. So imagine if a result you get by applying mathematical logic, it gets very easy acceptance. So this is one great example, and this led to plate tectonics. I think my research life started around 65 when this diagram came. And then his student Dan Mackenzie and R.L. Parker, they applied the same idea for Pacific Ocean. So they said that the Earth's surface is moving rigidity, and they could explain by applying this. And these arrows you see, they came from earthquakes. When earthquakes take place, they give you the motion, what kind of motion is there. So these, so in 1967, it got acceptance of the plate tectonics. These two papers you can think of leading to plate tectonics. Oh. Okay, okay, so when this came out, how to build a model? It means there was some hot mega came out and moved away. So a model was developed that when magma came out, it has a fixed temperature. It came in contact with ocean, so temperature became small. And as time evolved, temperature changed. So as you move away from the mid-oceanic ridges, the ocean bathymetry goes down, heat flows goes on decreasing. So you could make a prediction. You could predict that if I go so much away from the ridge, this is going to be bathymetry, this is going to be the heat flow. So one could predict, and this was observed. Many ocean expedition led to that. Interestingly, this is the same equation which Kelvin used to calculate age of the earth. What Kelvin did, Kelvin measured the heat flow, he knew the initial temperature of the earth and found out the time. He got only 100 million years because this was a wrong model for the age of the earth, because in the earth it is not only heat conduction, there is a, okay, sorry, one important point. See that curve which you see about Atlantic Ocean, this work was done way back in 1962. That also talked of spreading. But really it was an important thing, but not enough, because that requires understanding of Earth's reversal, and for that those two equations were used, which I show on the right side. Second one is for magnetization and first one is for gravity. Okay. Okay, so below these plates, what happens? A circulation happens. So in order to make a progress, one needed understanding of this circulation. So how this understanding came? For that we need now Navier-Stokes equation. In Navier-Stokes equation you have circulation term. But this, so here initial work was what was done by, say, Jeffries, great S. Chandrasekhar. But they were studying stability problem, that you have a steady state solution, and when you perturb it, it goes to another steady state. But at that time it was not possible to evolve a trajectory of how things will go. So, so what happened in these equations later on, you added nonlinearity because you didn't linearize it. You added complex viscosity, because now if I have to do pure Navier-Stokes with constant properties, I am doing physico-mathematical work, only properties. But when I add composition, I get physico-chemical mathematical study, and that led to the kind of results which Professor Dasgupta was mentioning to you. Now, Dr. Dasgupta mentioned both names. Dr. Chandrasekhar's book on hydrodynamic hydromagnetic stability, he developed Vennard convection in great detail and applied to the, at that time, continental drift, not plate tectonics. And then when you apply this theory, then you write Rayleigh number is very high. It means Earth, marginal stability is in turbulent state. And the next stage happened that seismologists came out the tomographic picture of the Earth's interior, and that led to better model of mantle convection. But exchange of stability, which Chandrasekhar's book describes, Rayleigh-Taylor, Kelvin-Helmholtz, they have been used to explain the mountain building, which is, okay, I will skip this. Okay, so here when you add composition, then you find the circulation which is becoming very complicated. So all those inhomogeneities which Dr. Dasgupta was showing on the surface is also present at the depth of interior. So Earth's interior is also as heterogeneous circulating as was on the surface. So it requires complicated model of, okay. Now below mantle, what is happening at the bottom boundary condition of the mantle? There is an outer core, but it is electrically conducting. It means there I have to use, along with Navier-Stokes, Maxwell's equation also. So here you will see Navier-Stokes as well Man's equation. And there were these two great men, same man Bullard as well as Elsasser. Elsasser did PhD under Max Born and then changed into working in geophysics. First radiation table of the atmosphere was by him. So they solved this equation. They used Earth core like an atom and used all vector spherical harmonics to explain things. And now with a numerical result, you can come out with very complicated lines of force in the Earth's interior. But this is because of numerical result. No amount of analytical work will do it. But here there is no composition. And if you add composition, then Navier-Stokes equation, you see the term C enters. And this is the work of Ajay Manglik of National Geophysical Research Institute, where you see the magnetic field and current topography at the mantle in a very, and these results are because you are taking more complex, you are putting more physics on your equations than it was earlier. Okay, so that is about this. So now there are two emerging things out of this mantle circulation, and one is about climate change, how Earth's interior has been changing the chemistry of the Earth atmosphere, because it is CO2 goes out of volcanoes, as Dr. Gupta mentioned, and how life originated, means how sun has been converting rocks to life. Life has come out of rocks being pushed by coming out of energy. So what are the mathematical reasoning to go beyond that? Okay, so let us look at the climate. In the climate, please look at on the right-hand diagram, you have volcano producing CO2, then CO2 coming through rains with the weathering of rocks, getting dissolved in the ocean with calcium and sodium carbonate form and back again to the ocean, and those diagrams does again a metamorphic. So atmospheric chemistry is being long-term controlled by the Earth's interior. Only short time humans are controlling partly. And you had those equations of atmosphere have been solved. It is called, Richardson was something around 1926, he started numerically. So basically what is happening that we have a very nonlinear system of partial differential equation which we discretize and convert to a problem of linear algebra or a sequence of linear algebra problems. So, and that we can easily solve with the help of codes. So now most of the work is happening using codes to represent what is going on. You see Harold Urey towards the corner, he was the man who gave how CO2 is sequestered in the Earth. Long-term climate is stabilized by the Earth's interior by the process of weathering. Okay, and these atmospheric models, to start with, you had only atmosphere, then atmosphere, land surface, oceans, ice, then atmosphere, land. So imagine over 1970 to now, the Earth system model have been developed with a large number of subcomponents, and this has become really a a numerical exercise problem in our system that you use very large cores to understand it. But but maybe analytically sometimes less is more than more. Okay. This was about equation, but another field is which is called data-driven modeling. Here you have Earth system, you have observation site, then from each observation you have a time series, and then those time series are behavior at each node. You can link those nodes by connection matrices, and you can do like what Dr. Atreya talked of graphons. So you can use all graph analysis methods to find out what is happening based on data only, not using theory. And now, but best thing is use theory and data together. Then there will be better advantage. Okay. Now, how the life is being modeled? The key thing is process of autocatalysis. Whether you are doing RNA world or whether doing metabolism, the key thing is autocatalysis. And I think we had two beautiful talks in the morning about catalysis in great detail. But autocatalysis is where some of the products act as a catalyst in one reaction or a couple of reactions together. I'm not a chemist, but I know how to convert a reaction into system of differential equations. And then this becomes a problem of solving a set of ordinary differential equation. And you can see how reactant products are working. And where this reaction is taking place, it is taking place all those red places. In those red places, you get vents of hot material coming out. So there you have food, you have the temperature, and these reactions will take place. And over billion years, you built up molecules which led to life, and life was generated there and moved to the surface. Okay, and this life finally led to biosphere, where we are part of it. And the kind of model which you have biosphere are basically three kinds of processes which are used. One is exponential model, first equation. Second is logistic equation. And third is predator-prey equation. So whole biosphere requires multiple of them, combination of them, to model what kind of biospheric processes are going on in ecological. And these are the two very famous geologists. One is Russian, another is European, who were responsible for these ideas. And imagine biosphere starts from 11 kilometer depth all the way up to 12 kilometer. And the focus of current research is on that topic. Currently, we are focusing near the surface from groundwater to tree canopy. It is like a critical zone of a hospital, because from here we derive all resources and pump all our wastes. So here, what is happening, we are pumping energy, matter, and then there is energy is being stored, then dissipatic product. This is the language of non-equilibrium thermodynamics, which is a very advanced subject now, and this is being used to explain critical zone. Our country has just started also research in this area. And the kind of equations which you have to deal with is this. I have to have conservation of energy, which we had in case of mantle circulation. I have conservation of momentum, but it is a porous media. So I have to combine elastic and porous media together. That's why I have a Darcy law. And I have complicated constitutive relations with density related to temperature, pressure, composition, stress with energy and strain, permeability, viscosity. Then I have conservation of mass. There's a fluid and solid and conservation of solid. So in order to understand critical zone, the kind of mathematics we need, no amount of analytical work is going to do. It has to be done numerically. It's a advection, basically it's advection diffusion processes which are active. And in our models earlier, we will take a flat Earth surface as boundary condition. Now we take them to be deforming because rivers are sculpting it, hills are eroding. So this equation, which is called reaction transport equation, was the last equation given by Turing. Turing wanted to explain patterns which you see on the animals. So he wrote a paper on reaction transport, and this reaction transport is being used to explain how Earth's surface is changing in various ways, and how life is also included in the process. Now on the Earth's surface not only simple life live, there are animals and humans, and they are also changing the Earth's surface. How to model them? Now there is something called agent-based models, because humans have intention, electrons have no intention, though the language was very picturesque by Dr. Krishnamurti, but they have no intention, they don't have goal. But humans have a goal, animal has a goal. So how to include these models? So this is going on now, research. Okay, I'm coming to the end. There is a big attempt now, because using all these set of equations, all the data, to prepare what is called digital twin of the Earth. That in a computer, I can create a Earth with all the satellite data available, mimic what all goes on in the Earth, and if suppose I decide I have a conference here, what kind of climate is going to change because of this conference, I should be able to answer. This digital twin can answer that question. So that kind of decadal effort is now going on. It requires you to integrate algorithm with the computer design. You need to have algorithms which are sync with the design. Okay. This is the last, I'm coming to the end. Where maths is going. Now, I'm not a mathematician, but what I read from the literature, there is a program called Lang-Land's program. And if you recall Dr. Dhate's talk, he mentioned number theory, he mentioned harmonic analysis. Now, this program says that mathematics can be unified by combining number theory and harmonic analysis by symmetry. So symmetry conditions are very important. Now, very little work has been done about symmetry in the Earth's interior. There is a paper run by Dan McKenzie, who was originator of Plate Tectonics, and there he discusses that how different symmetry changes taking place in the Earth's interior. I wrote to him that I am giving a talk, I want to know what is your latest work. He said, I have done a lot of work but not published. He will come out it. So what is happening, that as Dr. Dasgupta was saying, that land surface configuration is changing. Is it a result of changing symmetry in the Earth's interior? Now, that will be possible if this Lang-Land program is successful. I have two things, very beautiful. I'd have no time to show to them, but if somebody wants to see, he should see this site. Okay, a bit of personal. I started research in 1964 at National Geophysical Research. My guide was Dr. Negi. We were 4 or 5 people. He called all of them, and he said that it was theoretical geophysics group. He said these are the 3 classical equations: diffusion equation, wave equation, and Laplace equation. Look all geophysics through the lens of these equations. So, as I showed you, that whatever result is strong has been backed by mathematics. Rest is, other is a story or not that organized knowledge. So, at a National Geophysical Research Institute, there was a great drive towards mathematization of Earth, and I pay tribute to my guide today. So how do I see future? Rise of coupled physical Earth and cyber system to understand Earth behavior. Earth behavior, I'm not talking only properties. Structure, properties, functions, performance, as chemists have been talking this morning. A material has many things than just structure or property. Find where it headed and steer where we'd like to go be. It's a very bold statement that we can steer Earth where it is going, but many religions see that we know where Earth is going. Nature of this development will be decided based on sensor and computational machines, focusing on multi-science, increasing component in Earth system and beyond. data-driven approach to answer immediate problems, and physics-driven approach for long time and long scales and long time scales. So physics we should use for smoothed models, but for detailed application we go for detailed numerical computation. And I end with my last comment by showing you Dirac. He said that I learned to distrust all physical concepts as a basis of theory. Physical concepts we praise. He didn't trust them. Instead, one should put one's trust in a mathematical scheme, even if the scheme does not appear at first sight to be connected with physics. The physical meaning had to follow behind the mathematics. So I hope in our earth science community, mathematical properties of earth system to precede geological concepts. We built geological concepts based on the mathematical properties of the earth which we observe. So my summary suggestion is earth system science will highly benefit by assimilating all possible mathematical properties in their investigations, and mathematicians and other scientists too, by looking earth system for newer ideas, as those great mathematicians had done in the past. Thank you very much.
Thank you, Rishi. Wonderful talk. I think it should, there will be many questions, I hope. It is a very interesting talk. It is transcending the boundaries of other sciences. Is there any talk? Anybody wants to ask any question here? No. Okay. People are hungry. Okay, they go for the lunch. I think we stop here. Okay. Thank you.